the time that we've advertised for the webcast to begin.
Is that working today?
It appears to be. I hope nobody heard that.
Have you gotten traction with yesterday's stories?
Oh, yeah, it's in Nature.
Well, I know
You know he's
Governor
coming.
15.
Okay, you know he's coming.
Well, we figured that he could get the first part of that and then rush up here. And he
Okay.
knows where it is.
Okay, so he might make a last-minute dramatic appearance?
Exactly.
Okay, fine.
Spooky.
Okay. I'm just waiting for the clock to turn to 11. It just did. It just did.
Countdown?
Yeah. All right. Welcome, everybody, to the Tuesday morning press conference here at the 232nd meeting of the American Astronomical Society in Denver, Colorado. I'm Rick Fienberg, AAS press officer, and I'll be the MC this morning. I want to welcome those of you who have tuned in via webcast and apologize again for the fact that our webcast didn't work yesterday. Today, thanks to our crack AV and IT staffs, everything seems to be working. And I hope I just didn't blow it by saying that. Helping me today, monitoring the webcast, is my AAS media fellow, Carrie Hensley, in the back. And during the Q&A, one of our Astrobytes authors, Gaurav Kular, will also be helping out with the roving mic. If you have a cell phone or a beeper or anything like that, make sure it's silent. Yeah. And there are two press releases that have gone out in support of this morning's briefing. So if you're on the AAS press list, you either have already received a press release or will receive it momentarily. Obviously, there's no webcast archived from yesterday, but the briefing presentations and the available press releases from yesterday's briefing are linked from the online press kit, in case you want to take a look at those. So the way these briefings work is I'll give a brief introduction, including of all our panelists, except for the one who hasn't made it yet, but I'm assured he's coming. And then I'll turn it over to the first speaker. They will hand it off to each other, and then at the end we'll do the questions. And because of the webcast, when we do get to the questions, I want to make sure you wait for a microphone so that the people online can hear you too. All right, I think I got through everything. All right, so today's presentations are grouped under the theme Stars That Make You Say WTF. And before you run off to my boss to get me fired, you should know that I'm not cursing there. WTF means where's the flux? And we have three presentations about two weird stars. And two of the presentations will be team presentations. We're going to be talking about Tabby's star, which you've undoubtedly heard of, sometimes referred to as the most remarkable or unusual or bizarre star in the universe, or at least in the galaxy, and also about Epsilon Aurigae, which is actually a naked eye star that is in the news from time to time. So the first presentation will be given by a team of high school students from the Thacher School. It's called Multiband Lightcurve of Tabby's Star, Observations and Modeling, and it will be given by Yao Yin and Alejandro Wilcox from the Thacher School, which is in Ojai, California. And then also talking about Tabby's Star will be Ava Bodman from Arizona State University. She'll be picking up the story with the transiting dust of Boyajian's star. Boyajian is Tabitha Boyajian, who is the namesake of Tabby's Star. And then Bob Stencel and his grad student Justus Gibson from University of Denver here in this beautiful city will be talking about Epsilon Aurigae, the brightest member of a new class of Disk-Eclipsed binary stars. So hopefully it won't get too dusty in here today. We'll keep the room clean, and even though we said WTF in the title, we'll keep the briefing clean too. All right? Okay, with that, I'll turn it over to Yao and Alejandro.
April of 2017, we started actually getting data on Boyajian's star. And by May of 2017, we officially joined a collaboration of more than 100 astronomers around the world to better understand this mysterious star.
So this is all data completely Thacher homegrown from our own observatory. It's completely separate from all other data that Eva will be presenting on. This is, although we have some data from 2018, we'll mainly be focusing on our data from 2017 for our discussion and analysis of this star. Again, we can see relative flux on the vertical axis and time in days, or the UCT date on the horizontal. And the first thing we can conclude is that what we call the Elsie family dips, which is the 4 dips consisting of Elsie, Celeste, Scarabray, and Anchor, seem to have happened within a longer range, about 1% dip, that, again, we don't know what's happening with. So we know from the pre-Elsie and post-Anchor dips that there's been something else going on. So on top of the very long-term dimming and the very short-term, few-day dips, we've had this about 6-month another dimming effect happening, which is, again, something that we'd like to investigate further.
So when we were when all the astronomers around the world were observing the LC family dips, something they discovered is the fact that light in different wavelengths are actually dimmed differently by the obscuring material of Tabby star. So in order to better understand and characterize this, we started observing on top of Johnson V band in G prime, R prime, and I prime bands in the Sloan second generation starting in June of 2017. And as you can see on the multiband Lightcurve over here, the shorter wavelengths, such as V band and G band, are dimmed more by the obscuring material. They have a deeper dip than the longer wavelengths, such as R band and I band. So this chromatic dimming, is what we call it, has been discovered by other astronomers before, but we believe that our own data can provide some new insights on the nature of the obscuring material. And we arrived at this new insight by calculating this quantity in which we called RV that we're going to explain briefly.
So RV, it's a very textbook sort of number, but in reality it's just flux ratios. In RV, it stands for the total extinction in V band over the difference in extinction between B and V band. So we drew up this little cartoon. It's not based on actual data. It's just to help explain it a bit better. So let's say we have, so we see extinction on the vertical and wavelength on the horizontal axes, and we see the red line is the extinction we'd expect at any given wavelength. So let's say we have our wavelength of V band and a specific extinction at that, and a different wavelength, B band, with its own extinction. All RV is the total extinction in V band over the difference in extinction, which we call EB minus V, of B band and V band. So what's really nice about RV is that, well, first off, it's very common. A lot of people use it. And we can also characterize it by saying simply that a larger RV means larger dust grains, and a smaller RV means smaller dust grains. We can reason this pretty easily. If we have a large dust grain, which is actually about a micron or larger, we would expect most light, or at least the light we're observing in, to be dimmed very similarly. So we would expect our denominator to be very small and our RV value to be very large. With smaller grains, however, we'd expect the difference to be very large and our RV value to be very small. What's also very nice about RV is that because it's a ratio, it simply characterizes the dust itself, not how much dust there is. So if we have a lot of dust, it'd just be a bigger number over a bigger number. Smaller, it'd be a smaller number over a small number. It's completely independent of the amount of dust that's actually obscuring the star.
So we calculated our RV value using our best sample dip anchor, which is the last dip in the LC family. We modeled the dip and took the interpolated peak dip value, which you can see over here, and simply took the flux ratios in different photometric bands to arrive at our final RV value, which is 3.1 with an error of 0.2. What is interesting about this value is that it is totally consistent with the RV of traditional interstellar medium in our galaxy, which is calculated by previous astronomers to be about 3.1. So we can confidently say that we believe the obscuring material of Boyajian star is consistent with interstellar medium dust. What is also interesting about this RV value is when we compare it to the work of other astronomers, such as Mohn and collaborators in 2017, in which they calculated the RV value of this long-term dimming effect over a year in 2015 and 2016, and the RV value they found for this long-term dip is about 5 or even larger, which means that the obscuring material causing this long-term dimming is totally different than the obscuring material causing these short-term dips, and they're of significantly larger grain sizes. And this makes us arrive at our final conclusion, which is the long-term dimming and the short-term dimming may be caused by completely independent phenomenon happening at the same time, and it's not just one single effect.
So in summary, we can say with our three main conclusions, that is the LC family dips happened within a longer timescale dip, of which we're excited to see if there's any kind of periodicity of. The anchor dip was likely due to to grain sizes very similar in nature to traditional interstellar dust, and the obscuring material during the short timescale dips and the long timescale dips seems to be completely different and may be happening because of completely different reasons.
That's all. Thank you.
This is a different program, right? That looks like Play maybe up there?
No, that got rid of it.
Oh, that probably just launched a new one. Let me try it again. There we go.
Oh, right there.
There we go. That one?
Yeah, that's done.
Yes.
Hello, I'm Eva. I'm a postdoc. Oh. Am I speaking? Okay, yes. Hi, I'm Eva, Eva Bodman. I'm a postdoc at Arizona State University. And I'm also talking about Tabby star. Hopefully I don't repeat too much of what's already been said. So my work is based on the data from the monitoring campaign that uses the Las Cumbres Observatory Global Network, Telescope Network. This is the observing campaign that Tabby Boyajian led that is supported by the Kickstarter backers. So thank you to all our Kickstarter backers. This science was made possible by you. So as part of the Kickstarter reward system, backers were able to choose names for the dips that were previously mentioned. So I'm going to be using them in this presentation, and I encourage you to use the names when you write up the star. So this is the Lightcurve, 2017 Lightcurve Boyajian star. So we have relative brightness over time with the dips Elsie, Celeste, Skarabrae, and Anchor, which I've highlighted in red, yellow, green, and blue. Elsie is actually a pun on the word Lightcurve because it gets abbreviated as LC. So in addition to these dips, we also observed evidence of the long-term secular dimming, this slow change that occurs over the LC dip family, reaching a minimum in July, and actually brightening above pre-LC levels in October before appearing to return to pre-LC levels. So in this monitoring campaign, we looked at the star at 3 different wavelengths, B, R prime, and I prime, which is blue, red, and near-infrared light. The reason why we do this, as they touched upon, is it tells us something about the material obscuring the star. If the depth is the same at all wavelengths, then the object is either opaque or really large dust grains. Small dust grains on the other side, on the other hand, scatter more blue light than red light, so the dips appear bigger in the blue band. And how much more light how much deeper the dip is in the blue depends on the size of the dust. So we can use the ratio of the depth at one wavelength to the depth at another wavelength to constrain the size. And we do that by comparing to models of how light interacts with dust at various sizes. So I measured the depth ratio, the y-axis on the left side, for different segments of the light curve to see how it changes over time. And as you can see, it changes a lot, which means the dust is also changing a lot. So each dip has its own depth ratio that is different from the depth ratio of the secular dimming, the white regions. And the secular dimming itself also appears to have a changing depth ratio, higher near LC and getting close to a ratio of 1 near around Angkor. On the right, I have the sizes that these depth ratios correspond to. So high depth ratio of about 4 indicates a grain size of about 0.1 micron. A lower ratio of 2 indicates 0.2 microns. And a ratio of 1 is anything larger than 0.5 microns. This size range is comparable to smoke particles, like from a campfire. So this dust is more like a misty cloud than like the dust you find in your home. These sizes I put up actually depend on the composition of the dust. So these sizes assume a rocky dust, like a really finely ground sand. But if we assume icy grains, they're about twice as large. And if we assume pure carbon or pure iron, then they're about half the size or less. So all the variable depth ratio means the dust cloud is extremely complex. There are different kinds of dust causing the dips, then the secular dimming, and also each dip has its own kind of dust. And it also appears that the secular dimming is caused by various kinds of dust. So there's a lot of different kinds of dust going on. And it's important to note that the dust in the cloud is not varying in time. What we're seeing is different parts of the cloud as they cross in front of the star. So we're just seeing different parts with different properties. And all these different kinds of dust is also consistent with interstellar medium dust, or ISM dust, because ISM dust also comes in a large number of flavors. So what does this tell us about what's going on in the system? Well, we know since the structure of the dust cloud is complex, that means there is some variation in how the dust is produced, either in the mechanism, like maybe we have some comets and then some asteroids, or we just have variation in what the source of the dust, like different asteroids of different compositions. And because the grain sizes are small, then they have to be newly created. Small dust grains get blown out of the system by the star relatively quickly compared to the timescale of these in like under years. So fast on astronomy timescales. What we don't know is the composition of the dust. So we have to assume a composition and estimate a size, but these data don't put any restrictions on what it could be. And partially because of that, we don't know how exactly the dust is being produced. So we still have no idea. But we have, the star is still a mystery. So in summary, the dust cloud obscuring Boyajian star is very complex and made up of many kinds of dust.
Well, first let me apologize for Justus being a bit delayed. He is a Choctaw tribe member and wanted to take in the indigenous astronomy section downstairs, but I'm sure he'll join us shortly. I just texted him. All right. Well, long before there was a Tabitha star identified, in fact, nearly 200 years ago, Johann Fritsch in Germany identified the bright star Epsilon Aurigae, right, fifth brightest in that constellation, as a variable, and in those days asked whether anyone else noticed the dimming, the nearly three-quarter magnitude of dimming that had occurred. But are we on screen? Not yet. And so that resulted in people kind of paying attention, but it took another 27 years before the star exhibited that characteristic once again. And so here's our summary slide. Last year I published a list of 24 additional disk transiting type stars, where Epsilon Aurigae is the brightest member by far. And many of those were found due to the wonderful surveys of the sky that are underway. In those cases, they can detect small changes, not just Kepler, but lots of diverse kinds of surveys. So I'll speak closer to the microphone. And I invite you all to come to our papers, joint papers, tomorrow, session 315, where we'll get into the observational data of recent times, as well as the stellar evolutionary model, which hasn't been adequately considered for decades, literally. So what's involved? Well, the bright thing is an F supergiant star, hard to miss, third magnitude. In fact, during the last eclipse, 2010, only the eighth time witnessed by humans, or recorded by humans anyway, we managed to get a big citizen science project going in collaboration with AAVSO, and a lot of people got to watch a star go through a noticeable amount of dimming for a 2-year period. Not these little dips you've been hearing about, but a substantial, lengthy eclipse. Tabitha is wonderful. I'm not dissing the star at all. So now, over time, people had speculated what was causing that massive eclipse. And from the largest star in the universe kinds of arguments down to a swarm of asteroids have been invoked to explain the nature of that particular light curve. Remember, it only comes around every 27 years. So last time, 85 timeframe, I was a mere postdoc working with Steve Marin at that point, more or less, or against him, hard to say. But 2010 got a second opportunity. We're able to use the Chara array to interferometrically image the dust cloud coming by, as well as obtain data from Gemini. So we've learned a great deal more about the disk. In fact, in particular, with Gemini high-resolution infrared spectra, we could determine that the carbon isotopic ratio is far from solar value, about 90 for the 12 to 13 carbon isotopic ratio, but it's way down there at about 5, which is characteristic of basically AGB type stars. More about that in our talks. So additionally, and this is where Justus would chime in, we've obtained a whole bunch of data last eclipse cycle, could identify a mass transfer stream. So this is a pretty active system. The F-star is boiling off. The companion is grabbing material, producing a big dusty disk. That sets some kind of timescale. You all should know about YSO disk timescales of order million years. So that kind of sets a constraint that after a million years, you might expect things to dissipate. So the argument, the debate for a long time, even the likes of Kuiper and Struve and others have weighed in on this historically, is what the heck is this opaque occulting thing? And of course, imaging it and through other infrared measurements, it's possible to identify it as a disk, presumably an accretion disk, shows all kinds of wonderful reddening, as you might expect from dusty material, but it also shows transient carbon monoxide. Now, I don't know of any YSOs that turn on and off their carbon monoxide. There's some variability, but here we saw a significant CO absorption event, which allowed us to get at that 13-12 carbon ratio in particular. And so the debate has been whether it's a supergiant that you would expect to be a 10, 20 solar mass star, and the mass ratio constrained by single-line radial velocity type measurements would argue that it's close to unity, or whether it's some kind of phony supergiant, and there's a whole class of those post-RGB, post-AGB type stars. Again, if you've followed the literature, you should be aware of those. But that post-AGB scenario means that the apparent supergiant could be a little wimpy thing, that is a core and a big envelope, maybe down in the single solar mass variety. That conundrum, that dilemma has been impossible to prove, except now the news is that the Gaia satellite in their second data release, DR2, has provided a 4 sigma parallax measurement. Caveat, second data release, recalibration, especially on a bright star, probably not the final word, but if the 500 parsec distance holds up, as opposed to speculation about it being 2,000 parsecs or more distant, if indeed the closer distance is true, it nails the system as a high mass ratio AGB-like object, and hence we can really resolve the rest. It requires there to be something like a mid-main sequence B star hiding inside the disk. Can't be too luminous or it would have blasted the disk apart by now. So we've caught it at a very interesting and very special time. And again, if you want more of the story, our papers come up tomorrow afternoon. So that's it for the moment.
Thank you very much, Bob. I think you did the talk justice.
Thank you. Well, there is justice in this world.
Right. Okay. So we're going to take questions now for any of the speakers. We'll start here in the room, and then we'll go to the webcast. If you want to ask a question, please raise your hand and then wait for Gaurav to bring you a microphone so that the folks on the webcast can hear you. And then identify yourself by name and affiliation and who you're directing your question to. All right, questions? We'll start over here with Chris.
Thank you. I'm Chris Lintop from the BBC Sky at Night. Question for Eva. The picture that you're painting is that the dust is recently produced, if I've understood what you're saying. How does that reconcile with the fact that the star's been dimming over more than a century with the plates? Is that recent in astronomical terms, or is something else going on?
Well, as they mentioned, the really long, century-long dimming appears to be made from much larger grains. So once you get above like 1 micron, then they're going to stay in the system long term. So it's only these like really small ones that get removed.
Other questions? Okay, down here in the front.
Steve Marin, freelance for any of our 3 Tabby star people. And just following up on Chris's question, if you didn't have the unusual grain size for the long-term stuff, would you know that it's associated with the star as opposed to some passing interstellar something?
If the long-term dimming was small grains, then it'd be, it probably would not be part of the system because it could not stay there for that long. It'd be more like ISM, like just in between.
I actually have a follow-up because I had a similar question. So this is Rick Fienberg from AAS. Do you have a mental picture? This is for any of the 3 of you also. A mental picture of what we're talking about here? Is this stuff close to the star? Is it part of the system? Is there an amorphous, clumpy cloud passing by? Are you able to say it must be, at least 2 of the following 3 kinds of systems, or, what are you heading toward with the data you have now?
So this goes mostly back to speculation. I mean, we really don't know what's happening. For all we know, there could be microscopic aliens.
Oh boy! You had to say that in a press conference. Yeah.
But realistically, we're not very sure whether or not it's really close to the system or really far away. Even if it is interstellar matter, it could be much closer to us than it is to Tabby star. It could be very close to Tabby star. We're just And again, that's just speculation. We don't know yet.
My pet idea is that it is circumstellar, but that's also where my research interests lie, so I want it to be circumstellar dust. So yeah, I think of it as like a clumpy amorphous cloud that's just kind of going around the star, and we're just seeing different parts.
Kind of like the ring arcs of Neptune, perhaps.
All right. Carrie, do we have any questions on the webcast? All right, we'll take some of those.
All right, this question is for Eva from Monica Young from Sky and Telescope. She asks, can you confirm that you are indeed seeing chromatic dimming on the 6-month timescale?
Okay, so secular dimming. That's highly uncertain because those depth ratios depend a lot on how you normalize the light curve, and since we don't know exactly where we should normalize the secular dimming, we can't really say 100% sure that it's chromatic, but we can say it does appear to be at least changing a little bit. But how chromatic it is, can't really say.
Any more online?
Mm-hmm. And
Okay.
we have one more question from Rick Lovett, freelance, and this is for any of our Tabby Star presenters. Can you clarify the timescale for dust removal?
It depends on if there are any alien housewives there. Okay, now I'm the one in trouble.
It gets removed within an orbit, so like
That
which
depends on the distance.
which
right?
depends on the
Yeah.
distance. So yeah, it's less on the scale of years.
Thank you.
Okay, we had another question in-house here, right? You want, okay, over here? Oh, well, okay, you do that one first and then we'll come over here. We got plenty of time. We won't miss you.
Hi, Fritz Benedict, interested bystander. We had a great talk this morning about molecules in space. Is there any hope of characterizing the dust with millimeter observations?
I think it's too faint. I think there has been observations in the millimeter, but it was all upper limits. We need something more like James Webb.
Fritz, in terms of EPSAR and its dust cloud, we attempted that with the Herschel satellite equipment, and no sign of spectral features, just a continuum. And sadly, it's too far north for ALMA, which could probably do it nicely.
We also believe that if we see another more significant dip, like such as more than 10% dip or the 20% dip we see in Kepler, it will be way easier. It will be another opportunity for us to do, for example, spectra on the star and get a hold of what the obscuring material actually is.
John, did you want to add something? No? Okay, let's bring it back over here then.
Hi, Jake Parks, Astronomy Magazine. So kind of in the same vein, I was just curious what the next steps would be to actually determining both the composition and sort of the origin of this dust. And it sounds like spectra would be the obvious next choice. And I guess, do we have a timeline on that at all?
We think that we are kind of just doing the waiting right now. Like nobody really knows what the star is behaving, and we're really just waiting for a more significant dip to happen right now. And I believe like more than 100 astronomers around the world are like monitoring the star really regularly, and that I think is really important. So if a really significant dip happens, we will be able to catch it immediately, and more information will follow that.
Okay, down here in the front row. Wait, hold on, wait for Mike. Thanks.
Tom Ayers, interested house husband. This is for Professor Stencel. So what happened to all the mass of the F supergiant? Should it be lingering around in some kind of shell that we could observe?
Right. That's part of the MESA model calculations we've done, and the mass loss would have been as much as 3. Try as we might, with infrared methods to find that mass loss. There is a dark cloud in the vicinity. Whether the travel over millennia is sufficient to associate it, still TBD. But producing that extreme carbon isotopic ratio strongly implies an evolutionary history that's been long enough, potentially, for some of that to be lost. It's in the galactic plane, so it's a messy part of the sky to try to separate. But spot on question.
Thank you. Eric Mack from CNET. Just really quick for Yao and Alejandro, what are your plans for the next year or two in terms of school, and if you're going to be continuing to study this?
Well, I've been thinking about Tabby star a lot, so I haven't been thinking about that too much, but astronomy sure seems really fun, and sure would like to continue with it. But we are rising seniors, so we're still in the process of applying to college and everything, so it's a little uncertain.
What does rising seniors mean?
So we will be seniors next year.
Oh, okay.
As opposed to failing or falling.
For me, I guess I'm not exactly sure. I guess I love astronomy, it's space, and I'm very happy to continue working with it. In terms of in the future during college, that's still up in the air.
All right. Do we have any more questions on the webcast? All right, I had a couple questions, unless there are any others in the room at the moment. Okay, I have one for you, Bob. When the next eclipse begins in about 20-ish years, what data are you most interested in gathering, and what kinds of instruments that we know are on the horizon for that time scale do you anticipate turning toward this star?
Right. The most interesting phase of the eclipse, in my opinion, third contact. That's where we see the stream impacting the disk and some amount of low-energy fireworks going up. And that occurs roughly in the 2037 timeframe, so mark your day timers and such. And it'd be good to try to confirm the isotopic ratio. Be nice to measure a little more detail of that mass transfer stream. In our previous work, we've found interesting little tidbits like the enhancement of rare earth elements in the stream, which is probably a radiative transfer effect more than an actual abundance thing. But it's kind of fun to see all those rare earth elements that our invited speaker yesterday referred to perking up. So there's a lot more to this star than has been sorted out so far.
Okay, and then a question for the Tabby cognoscenti. It sounds like the cloud itself the dust itself is too faint to get an emission spectrum from. But since the cloud is moving in front of the star, are you able to get any information out of absorption by the dust, other than just the basic color differences? Are you able to get any clue as to whether it might be more silicate dust, more carbon dust, more rocky, more et cetera?
We only have spectra in the visible, and that didn't show any change during the dip.
So you need broader wavelength coverage to be able to get that?
Probably in the infrared.
Yeah, okay. Okay, another one from Fritz in the back. Fritz is not just an interested bystander, he's the secretary of the AAS.
So there are these things called diffuse interstellar bands. Has anyone looked for them associated with this dimming?
Not that I'm aware.
Not that we're aware of, no.
They do appear in the Epsilon and Aurigae spectrum, but are consistent with interstellar distance path, along with things like potassium, neutral potassium.
Okay, anything else online? Okay, we do have another one online. We'll take that.
This question.
Yeah, you're live.
This question comes from Rick Lovett, freelance, and this is for all four of our presenters this morning. What can comparing these two stars tell us, if anything? Are they just both oddities in the universe, or are they oddities that can help us see a bigger picture?
Tabbies?
I mean, I think any oddities we find, it can help us understand what's going on in the universe more, because, anything out of the ordinary, anything that we have to research further, it gives us more insight into what's happening in the universe.
Anything to add, Eva?
It sounds like Yao maybe.
Sorry,
summed it up
Yao.
very
Yao,
well.
did you want to add something?
Yeah, kind of what science is. You don't know what's happening, so you look more into it. And I think with the new missions such as JWST and TESS coming up, we will definitely get probably more oddities like this, and we'll certainly learn much more about our universe in the next few decades. So I think it's really good.
Tabby star is, probably an oddity, but oddities tell us like the limits of what can happen, so they're always worth looking into.
Well, the other thing is, well, you go ahead, Bob, and then I'm
Okay.
going to add something too.
Well, I can't speak to Tabby star. I don't think we know enough about it yet. But Epsilon is clearly the member of a class of stars called Algol-type binaries. And, of course, the Algol paradox has already taught us a great deal of things. In the current era, the students here will be able to compute mass transfer models in binary stars and explore all of the interaction. And if you were listening to invited talks earlier this week, the production of merging neutron stars ultimately seems to trace back to common envelope involution in binary stars. So any number of these systems has the potential to grow up into a gravitational wave source, for example, as well as producing heavy elements, as was mentioned earlier. So there's this much bigger context. And also, of course, we've recognized not just transiting planets, but the presence of circumstellar dust and disks all over the place. So it's just falling into context, finally.
And I just wanted to add that, Tabby star came up in the Kepler survey, which was just looking at one very tiny part of the sky. And TESS, although it won't be looking out as far, will be looking around the whole sky, and future surveys will continue to be looking around the whole sky. And so I think that, even if Tabby's star, well, everything is unique by definition, but I'm sure there will be other systems like it that turn up as we look, much more broadly around the sky with this high-resolution photometry.
Already have.
Yeah.
They have turned up.
Yeah, so it'll be interesting to see. Okay, any other questions? Any more in the room? Last call? All right, well, if not, I'd like to thank our speakers again. There's a lot of very interesting stuff. Our next briefing is this afternoon at 3 o'clock here in the same room. It's on metal poor stars, dwarf galaxies, and a cosmic conundrum that goes even beyond Tabby's star or Epsilon Aurigae. Thanks for coming, everybody.
Certainly.